Hi, welcome back. We have another question based on polyfeed and polyval function that we have seen in the last video. This question has temperature and density data, and we need to fit this data in first order through fourth order. That means first, second, and third and fourth, all of these polynomials. And we have to interpolate the value of density at 375 Kelvin. You can see that at 375 Kelvin, no density is provided. So we're gonna have to interpolate that. That will be our first problem. The second is we have to use first order and third order polynomials to generate the predictions of density between the temperatures 200 to 500 with the increments of 1. That means we'll calculate the density for first order and third order polynomials for 200, 201, 202, 203 and so on at all the temperatures. Okay, and then we're gonna have to plot those three data for linear, one order, third order, and the experimental data that is given to us here. Let's go to MATLAB and see how it's gonna work. Create a file. Let's just call it temperature and density. Okay, store the temperature and density data very first. I'm gonna call row temperature data. Okay, so the temperature has 50 gap, right? What I can do is I can tell it is starting at 200 to 500 with the gap of 50. So gap is 50 until 500. Let's just see if it works. It did. So T has all those values. Perfect. This is how you can basically initialize your temperature, initial point, the final point, and the jump that you want between subsequent steps like 200 to 250, then 250 to 300. Anyways, let's just put row data. I don't think we have any linearity in this case, so we have to just copy paste it. Okay. Okay, we have our temperature and row data. Let's polyfit it. So the coefficients I'm gonna store in coefficient function, coefficient variable, polyfit. The x data is gonna be t and y data is gonna be rho. Okay, and I'm gonna fit it in first order first, and then calculate new density row, interpolated density value, polyval, pass it the coefficients of your polynomial, and yeah, at what temperature you want to interpolate. At 375 Kelvin. Everything looks good. Let's see. Okay, so at 375 Kelvin temperature, the density is 0.9998 between, oops, here, which seems, I don't know, maybe that's how it's interpolated. So anyways, this is how this is how you can basically fit the data in first order. If you want to fit in the second order, one thing that you can do is copy this code, paste it, and just change this, okay, and run it maybe again. And this time when you fit, you get better approximation, you see better interpolation value. And you want to fit in the third order, you can just copy paste again and do that. Okay, and the third order approximation is, I guess it's even better, but I'm not sure. So this is not good, you know, because you want to calculate the same thing again and again. What you can do is you can use a loop. That's way much better. So because we are going to have to calculate, you know, density value at 375 for 4 different problems, like we have for the first order, and then through first order through fourth order, right? So let's just create a loop and run it 4 times. And okay, and also you need to change this in each loop. This number has to be changed, the order of polynomial. So I is the best appropriate value here. And also you need to print the value of density, because you're calculating in each loop, and if you don't print it, it's just gonna overwrite your row value. So there's no point in running loop in that case. So let's just display the value. How do we want to display? Okay, let's just copy it. This is how we want to display, right? The estimated value of density using first order approximation or polynomial is the value and then this, maybe up to period. Here I need a number, sorry, I string. So I'm gonna have to convert that number which we have calculated here into a string, row new, and then print that and take a space and print the unit. Perfect. This should work. Oh, add a comma so that it will suppress the output each time. Okay, you can see that for first order we are getting data almost 1, and then I think it improves as you increase the order up to at least third polynomial. Okay, also this is 2-line code, right? And if you don't want 2-line code, what you can do is you can do the whole thing in 1 line. Let me show you. You want to calculate row new, right? This is what you want to calculate at 375. So you can directly use polyval, and inside it, this is where you write coefficients value, right? The coefficient is equal to this thing. So let's just copy that whole thing and pass it here, and then comma, at 375 I want to calculate the temperature density. That's it. So this 1-line code is gonna be equal to this 2-line code. So I'm just gonna remove this. Too many spaces. Anyways, leave it. Okay, now it looks clear and clean. Perfect. Okay, so that was the first part. I don't like these extra spaces. Okay, so that was our first part. Now what we need to do is, for the first order and third order polynomial, we have to generate the density data for temperature ranging from 200 to 500 Kelvin. Okay, let's just take maybe T smooth, and it contains values from 200 to 500. So with the increment of 1, this is like by default increment is 2. If you want the increment, by default increment is 1. If you want the increment, let's just say 50, you can write this, or maybe you want increment of 20, you can write this. This is the increment in the middle, okay? But we want 1, which is default, so let's just leave it. T-smooth. Okay, now we have all the temperatures, and also we need to calculate first order polynomial and third order polynomial coefficients. So let's just say row from the first order polynomial, so row first I'm gonna call it, and just copy this data of code, polyfit row I instead of I, because it's first order, and instead of calculating the row value at just 375, we're gonna have to calculate it over a range of temperature, right? So let's just provide that range of temperature. That range of temperature is T smooth, right? So let's just give it T smooth. Okay, perfect. The same thing we're gonna have to do it for the third order polynomial. I'm gonna call it third, and I need to change here third. T smooth is same for both of them. Okay, so this line of code will interpolate the density data at these temperatures and store that vector, all those density corresponding densities, in row first. And similar is true for this particular line of code. Okay, now we have all of this data. Let's just plot them. Oops. First, let me show you how the plot of real temperature and row looks like. Okay, come on, I don't need this. So this is the experimental value, the data that is given to us. This is how the curve looks like. Okay, what I wanna do is I wanna print the next plot on the same figure window. So that has to be done by hold on. This time I'm gonna plot maybe the linear curve. The data is stored in row first. So temperature versus row first. That's it. Let's run it and let's just give it some different marking style. There's a problem, maybe this does not work. Come on, not circle, maybe star. Oops, this is the problem, not that one. Come on. The vectors must be the same length. Oh yeah, the vectors have to be of the same length. Row first contains, I don't know how many data. Row first, here it has 301. This is the length of row first, right? And the t has length of 7, so it cannot be plotted. What we actually need is t smooth, which has the same dimension as row first. So that was my mistake. T smooth, that's what we need here. No, not here. Okay, let's plot this one. Oh, this looks good, but I don't like this star thing. I'm just gonna choose different marker. Clear everything, clear the window and run. Okay, this looks good. So you can see this is the actual data plotted and this is the linear fit which is plotted. And then we're gonna plot, why don't I just copy paste? T-smooth row third. Row third data, I'm gonna plot. How do I wanna plot it? I don't know, maybe just a star. No. Maybe print. Okay. So you can see this yellow line, I think, is the third order polynomial fit data plotted. So you can see that this third order polynomial fit data closely predicts the experimental data. So yeah, that was it. We have successfully completed our question. Yeah, I'm not gonna print any star mark. Anyways, thank you for your time. We'll see you again.